So we're back here to take some more implicit derivatives. Just the more examples you can do of these, the more exposure you have, the easier it will get. So here's some function x cubed plus xy plus y cubed equals 1, and I want to find the equation for the tangent line at x equals 1. Okay, well, before we even get started with doing calculus, when x equals 1, we we have this equation, and we want to find out what is y when x equals 1. So we need to find out the y value when x equals 1. So solving this, I get y cubed plus y, and moving this 1 over equals 0. So y times y squared plus 1 equals 0. And the only real solution to that is when y equals 0. So when x equals 1 and y equals 0. So I want to find the equation for this tangent line. We're talking about this tangent line, right? That tangent line right there. So what we need to do is do implicit differentiation. So let's take the derivative with respect to x of both sides. And up here, we're going to need to start using some of our new rules, product rule and chain rule. In this case, just the product rule. So right-hand side, we know the derivative of a constant is 0. Left-hand side, working our way across, the derivative of x cubed is just 3x squared, dx dx, so that's just 1. Plus, now we need to do a product rule where that's my first function, and this is my second function. So the derivative of x, so taking the derivative of x first, derivative of x is 1 times y plus x times the derivative of y, which is dy dx. And just to kind of make sure that this component is clear, what we had is xy, where we said f equals x, f prime equals 1, g equals y, and g prime equals dy dx. And so we got 1y times x dy dx. Okay, now we need to take the derivative of that y cubed, and we know that that's going to be plus 3y squared using the power rule times dy dx. Okay, so once we get here, now we need to solve for dy dx. So let's move everything without a dy dx over to the other side and factor out a dy dx. We get dy dx times, or parentheses, x plus 3y squared equals negative 3x squared minus y. And then dividing, we get dy dx equals negative 3x squared minus y over x plus 3y squared. And that's our derivative for any x and y value. But we want to find at this specific point when x is 1 and y is 0. So plugging those values in, finding dy dx at the point 1 comma 0 is going to equal negative 3 times 1 minus 0 over 1 plus 0, which is negative 3. And that slope makes sense, given the slope of my tangent line. But then I need to actually find the equation for the tangent line. This is my slope. The equation for a tangent line is y equals m x minus x1 plus y1. And the point that we're looking at is x is 1, y is 0 with a slope of negative 3. So our equation is y equals negative 3 x minus 1 plus 0, or negative 3x plus 3. And it's very clear that, looking at my tangent line, that's exactly what that is. So I'm getting I did all the algebraic work, but then I'm comparing it to a graph and making sure it makes sense. Let's do another implicit differentiation problem. Here's the graph. I'm going to make it a little bit smaller so that I have room to do some work. And we want to find the slope of a tangent to a curve at the following point. And I think more than just find the slope of a tangent, let's find the equation, just to have more practice. Finding the equation of a tangent to the curve when x equals 1 and y equals 2 pi. So we're talking about this equation of the tangent line right there. A little bit tough to see, but more or less, I guess, close enough. So we want to find the equation for the tangent line. We already have the point. Now we just need to find the slope of that tangent line. And we know that to find the slope, we need to find the derivative. And since this is an implicit equation, we need to use implicit differentiation. So we're going to take the derivative with respect to x of both sides. And here we have both the product rule and the chain rule. Okay, so looking over at the right-hand side to start off with, I know that we've got a pi in there, but 2 pi is just a constant number. Pi is a fixed number. So the derivative of a fixed number, is, once again, 0. And then if I look over at the left-hand side, I've got the derivative of x squared y plus the derivative of sine of y. And let's, here we've got one function, x squared times the other y, and over sine of y, I've got sine of y. So here we're going to have a composite function. So taking the derivative, let's start off, left to right. To take the derivative here, it's the first times the derivative of the second plus the derivative of the first times the second. So that's this is this plus, well, we've got sine of y. So the derivative of sine of anything is cos of that thing. And now we need to take the derivative of the inside. So the derivative of that inside is dy dx. And that all equals 0. So this is that. Okay, so then last step, always we're going to have here is to factor out dy dx and isolate. So when we do that, we get dy dx x squared plus cos of y, and this is going over here, equals negative 2xy. So simplifying, dy dx, or our slope, equals negative 2xy over x squared plus cos of y. And we're evaluating this when x is 1 and y is 2 pi. So this is negative 2 times 1 times 2 pi over 1 squared plus cos of 2 pi. And luckily we know our unit circle very well. We know cos of 2 pi is just 1. So this is negative 4 pi up top over 1 plus 1, which simplifies to negative 2 pi. That's our slope. So we found our slope. We have our point. So the equation for the tangent line is going to be y equals m, our slope, x minus x1, where that 1 is coming from there. The negative 2 pi is our slope, plus y1, where y1 is 2 pi. Simplifying this, we get negative 2 pi plus 2 pi, or negative 2 pi x plus 2 pi plus 2 pi, which equals negative 2 pi x plus 4 pi. And that's the equation for our tangent line. So I think we'll do one more of these implicit differentiation problems. It says, find all the points where the tangent lines to the graph of this are horizontal or vertical. Well, where the tangent lines are horizontal or vertical, where they're horizontal here and here, that means that dy dx equals 0. And where they're vertical, that means that dy dx is undefined. So to do that, let's find an equation for dy dx. So let's do some implicit differentiation. We're going to take the derivative of x squared and the derivative, so the derivative of the left and the derivative of the right. And when we do that, on the left, we're going to get 2x equals, well, the derivative of 4y is 4 times dy dx, minus the derivative of y squared is 2y times the derivative of y, which is dy dx. If we factor out a dy dx, we get 4 minus 2y equals 2x. Solving for dy dx, we get the dy dx equals 4 minus 2y over 2x. So now taking our equation that we found, it's going to be horizontal. The only way it can be horizontal is if the numerator equals 0. Because the only way that dy dx can equal 0 is if the numerator equals 0. So we want to know, when does 4 minus 2y equal to 0? Well, that's going to happen when y equals 2. So where does that happen on our shape, on our circle here? Well, when y equals 2, going into our equation, we have x squared equals 4 times 2 minus 2 squared, or x squared equals 4. And remembering plus or minus, this is going to happen when x equals plus or minus 2. So we're going to have horizontal tangent lines at 2 comma 2 and negative 2 comma 2. Right now, people should be screaming at me saying, "You moron, you are so stupid." Hopefully you caught my mistake. Uh, when we, as I was going, I realized I was doing something wrong. When you divide by dy over dx to isolate it, not when you isolate dy dx, you should have gotten 2x over 4 minus 2y. Ah, that makes sense now. So for us to have a horizontal line, again, the numerator has to be 0. So when does 2x equals 0? That's going to happen when x equals 0. And what are my y values there? Well, if I put 0 into my equation, I have 0 equals, factoring out a y times 4 minus y. So that's going to happen when y equals 0 or 4. So in other words, I'm going to have horizontal tangent lines at 0, 0 and 0, 4. And for me to have vertical lines, for it to be vertical, the following needs to be true. So to have the vertical tangent lines, that would be that the denominator would have to be 0. So we set the denominator to 0, because that would make my slopes undefined. We find out that y equals 2. We substitute that into the original equation to find out what x equals. And then x is plus or minus root 4. So we're going to have vertical tangent lines at 2 comma 2 and negative 2 comma 2. And that corresponds to what we see there. So there we go.